want to discuss the quantum Merkle tree, which is what we propose in this paper. So here one wants to commit to a quantum state instead of a classical bit string. So you have a density matrix on capital N qubits that you wish to commit to, and one breaks this into L blocks of size B, where B is the security parameter. So you want to analyze the protocol with respect to how it scales with B, as well as other parameters. But B is a parameter called the security parameter. Now, quantum states are very different, as we've discussed previously in previous blog posts. In particular, we cannot copy them. And if we measure the value of a qubit once to check its values, then we lose the coherence by the virtue of measurement procedure. So it's subtle to use to be able to generalize Merkle trees to the quantum setting. It has some extra security, but is more subtle in the sense. So what we do use, however, is reversibility of quantum computation, as we'll see in a second. So the prover again has this n-qubit quantum state, builds a Merkle tree where every one of the non-leaf nodes are initialized to the tensor product of all zeros over b qubits. And that's important in this case. It's actually, it does matter that we start with all zeros. And also picks an order. So say, just like before, from left to right, and then layer by layer upwards. And instead of a hash function, so if you use a classical hash function, that just won't work because we have quantum states. Now, there are ways to encode the value of a classical hash function into the register, but we could see that they're also not safe against phase attacks, for example. But what we do propose is take G to be a random Haar unitary. So it could be seen as a very non-local circuit, or it could be built from a very deep circuit. It's actually an open problem what kind of whether we can replace G with a random circuit. I believe we can, a random circuit of, say, polynomial depth. So instead of applying a hash function, now you apply a G, which is a random Haar unitary, to these registers. So starting from 0, once you apply G, you end up getting a very entangled state, spreading it all over these 3B qubits. And continues like this as before. Now the second block, you see I replace them with stars because these are some states. So the whole thing is in some random state, and so forth. You keep going like this till the very end, and we call the value, so the set of qubits here, so now you have a box of qubits, B qubits, that's called the commitment in our scheme. And you send this to the verifier. So P just sends this to the verifier. P no longer has access, the prover no longer has access to commit psi, and V is holding these set of qubits. Now V wants to verify that the state here, this density matrix psi, is intact. How can he or she do that? Well, just like before, it can ask for block 2. So it's a set of qubits. It just sends a message to prover saying, look, I want block 2. Send me what you should. And P will send the following qubits. It sends the siblings, ancestors, and siblings of the ancestors of the Merkle tree that leads to block 2 of qubits. So it sends all these qubits to commit. All right, now commit from before had the root in its hand. Now it has these qubits shown in red rectangles. How is V to verify that these qubits are intact? Well, that's when the decommitment phase starts. And the decommitment phase does the following. It applies, recall that G and its inverse are known to both V and P a priori. Before the protocol starts, they agree on a G, which is a random Haar unitary, and its inverse. So it starts applying G inverse. It already had commit. Now it received these two, applies G inverse. If it ends up getting zeros everywhere all the way to the root, it will know that the quantum state was not meddled with, and it'll accept. Note that it's very important that we started from zeros or something fixed, and you decommit by running G inverse, and at any point that the verifier sees that he or she gets something other than 0, it rejects and says that, the protocol is broken. As an example, imagine if here block 2 had been meddled with a little bit. Then if you apply G inverse to the joint state of these 3B qubits, because of how entangled they were, you will not end up getting 0 in this first parent root. Well, not root, but the first ancestor of block 1 and 2. And that's a way for V to verify. And note that the whole protocol is succinct with respect to the number of qubits sent because of the tree structure here. So this is a commitment scheme that is also succinct. Now, in terms of proving its security, there are a lot of open problems I'll discuss. And there's another interesting problem, which I mentioned earlier, and that is whether we can replace G with a quantum circuit and prove security with respect to that. All right.